Anybody here familiar with New Relic? Customers? Yeah, so let's go back. Our product suite is a bunch of software analytics. It started as APM for Ruby and grew out of that. About 8 years ago, we started there. Java, we do some instrumentation inside browsers, which is really nice because then you can see end-to-end performance. All of that's great. We sell this as a service. We host it. It's multi-tenant. So basically, our product is a DDoS against us. It's this is what it looks like. What you can see is you can see some performance. This is average, unfortunately. Average is, you know, and some throughput numbers. And we get that by collecting lots of data from your applications. We get about 16 million posts a minute. A bunch of it is metric data where we measure things and aggregate it over that minute and send that to us. And we also do discrete events. In terms of metrics, we get about 800 million metrics a minute and about 3 billion data points that we query when we're looking for things in the analytics space. To do that, we have a system, there's a couple hundred microservices, a lot of on-disk storage occasionally. We basically collect data, we write it into a database, and then sometimes people look at it. It's hard to guess, measure, understand. About 1% of the data actually gets looked at from the database, but we collect all that data and store it because when you're having a bad day, you want to be able to look back and see what was going on before, so we have it. We rely on Kafka a lot. We ship data around our system. The green boxes are kind of the ingest pipeline. The blue boxes are other things after the ingest, but we rely pretty heavily on Kafka. I just took this, I don't know, 15 minutes ago. This is the last 3 days in our Kafka system. We do about 0.5 petabyte a day through Kafka. So the one thing that people don't usually look at when they measure their Kafka is kind of what's going on in terms of replication. So inside Kafka, we move as much data as we do kind of in and out. I guess it matters. We looked at this. We were going to move to AWS. This is all hosted in our data center. We were going to move to AWS. AWS charges you like a penny a gigabyte to move data around. This here is, I don't know, 500,000 gigabytes or $5,000 a day just for networking in AWS. This is kind of what our data ingest history looks like. We've been growing at a rate of about 2x every 9 months. So in 9 months, it looks like that. So that number that was way up here is now suddenly kind of ordinary, and it's going to go back up, and there's another 9 months. And right now, our model for processing data isn't going to scale with this. And we'll show that in the results. So what I want to do is I wanted to evaluate some streaming systems and understand their performance and operations characteristics, more focused on performance than operations. If it doesn't cut it in terms of performance, I don't care about the operations. We have a system right now where I would say it's adequate. We have adequate performance and we have adequate operations. We're looking at that as a bar. That's not a super high bar, but we'll see that not everybody makes it. So this is how New Relic works, kind of in the cartoony version. You've got your application, several instances of it running somewhere. You add our agent to it, and it reports data to us. And it sends us this kind of information. Oh, let's go back. It sends us this information, a little bit of identity information, what time period the report covers. So this looks kind of batchy, but we get 4.5 million of these a minute. So it doesn't look very batchy to us. It looks pretty streamy to us. But they're bundles. So you get this bundle of time slice data where it's a name, which is kind of scoped in like directory name scoping, and some small amount of statistics account, the total time that so think of these metrics as covering some piece of the execution of your program. So this total time is, you entered the function and then you left. And exclusive time is you entered this function and you're doing something here. And then the time that's different is it's covered in another metric that covers a trace. Mins and max, and an attempt to capture some variance in a sum of squares. So how does that apply? These charts are drawn from those metrics. And what we see is we can get throughput and response time from the same metric, same time slice, by applying different kind of ways of interpreting the data. So throughput is count. Just add up the counts, and you get that number. And then response time is how much time are we spending doing it divided by the count on average. To do that, we have a pipeline. Again, it's a little cartoony, but it's actually fairly accurate. So we get this data from the agents, and the first thing we do is we terminate the HTTP. We put it onto Kafka. So until we're done with HTTP, that data's somewhat at risk. Once it's in Kafka, then it's safe, and it'll end up in our database at some point and down the line in the rest of the stream. So like I said, a little bit of identity information and this other stuff. The first thing we do is we convert that token into kind of its actual values. And then we timestamp it with an ingest time. So that looks like ingest time maybe if you were using some of the Flink terminology. I think that's one of them. There's processing time and event time and ingest time. So that looks like ingest time, but it's really event time. We don't trust your clocks because your clocks are useless. They're wrong, they're not synced. You have it running on several hosts and they're just not going to be right. That's a scar. So in the past, we've tried to trust your clocks, and we don't now. So we get this, but this is event time in Flink terminology. This is the time that matters. And then there's this collection of time slices. So this time slice resolver's job is to kind of reduce the namespace of the metrics. So sometimes you'll get reports that'll have URLs in them, or segments of URLs, like account/1 and account/7, and those will just get starred out by that process. Because you don't really care how long it took to process account 1 or account 7. You really, it's like, my account processing takes this amount of time. And then we take those names and then we convert them into IDs. So the ID is a hash of the name. It's a 64-bit hash. It's kind of the low half of a 128-bit hash. The reason we do that is at the rate of data that we get, we're a lot happier having kind of a fixed size 8-byte name. So the names, I did some statistics on the names. The names averaged about 130 characters. And this package here averages about 18 bytes. So we get 18 and 8, so 26 versus 130 just for the name. So that would blow out our Kafka system. It turns out that's somewhat irrelevant, but it's useful to know in the next step, which is that we take that collection. Let me go back. I don't think back works so well in animation in yeah. All right, we'll get there. I went one too far. I missed a point that was kind of important. So when I showed you that picture of New Relic, that was the overview of your application. So that's the aggregate of all the instances of your application running. You can break. All right, I'll move on from that. So let's ignore the picture that's up there for a second. You can group your instances into different collections. So usually they're grouped into one collection, like my cool application, and it's on 10 instances. But maybe half of that is I process things in the background and I process things in the foreground. So you could break them down that way. What we end up with in this aggregator is we aggregate the metrics across those different types of breakdowns. So we'll get an aggregation for this instance, because you might report more than once in a minute. Or you might be using Ruby, where you have a forking server, and this host has 10 instances, so we get 10 reports from that host. And we glue that into one. And then we also do this synthesized roll-up version of it, and we treat them all like they're agents. And we change the distribution of the traffic. I don't even know. Anybody like animation? I can't. We changed the shape of the output because that's what we're going to write to disk. So by doing it here, we can spread it out later. And it turns out that other downstream functions that use that, it's very happy to have the difference in the start duration, time and duration, and kind of the aggregated things handy in one place instead of having to recompute it. Then it does the stream thing, and it goes to an hourly aggregator, which does somewhat of the same idea, except it turns it into an hour. We do that now because that's the data we keep for a long time. So the minute data we keep for about a week, the hourly data we keep for about 3 months, maybe more if you pay more. I'm not really clear on that. And then all of those things are streamed to a writer. So we need to separate kind of the speed of aggregation from the speed of writing to the database. But conveniently, by being in Kafka, we can actually do some downstream processing of it. So the experiment that I wanted to do, I came to Flink Forward last year. It was cold. I'm glad you guys paid for the heat this year. And I was stunned. I mean, it was amazing, and it maps really well to our problem. But I work with a bunch of skeptical engineers. So they know the thing they have. This thing is new, it's scary, it's dangerous, it's different. So I picked an application where I thought it would be pretty easy for us to be able to do an experiment where we could do a bake-off between our current model and some of the other streaming things. So I picked that minute-level aggregator. That's the thing that sees the most pain in our system. I picked it for a couple reasons. One, it doesn't have any external dependencies. It only needs to operate on the data it receives. It takes the data it receives, it reshapes it, and then sends it downstream. So we could totally focus the outcome of the experiment on the performance characteristics of the framework that we're experimenting on. It's very repeatable because I can just stick the same stuff back into Kafka and repeat it. So I think that comes as a side effect of the external dependencies, but it's a dimension of its own that's important, and it's important to our business. It turns out that, I don't know what that line is, that's a typo, but we could have benchmarked something else, but it really didn't have, that would just leave more questions. Like, well, yeah, it does well on the Yahoo benchmark, but who cares? We don't do the Yahoo benchmark, we do aggregation of time slices. So by picking a problem space that's in our domain, it kind of validates the response. We could have done our aggregator as well. It has similar characteristics. But the problem with the hourly aggregator is you got to let it run for a couple hours just to get any insight into what's going on. And I'm frankly not that patient. So I did a little extra credit, though, work to see if I could integrate hourly aggregation and minute aggregation in the same Flink topology. And I'll cover that if we have time. So the goals here, with respect to understanding performance, the thing that I wanted to look at was arrival rate of events. And in particular, I picked this kind of strange number. And if I press the right button, it'll work. So 6,000%, like what? Why would you pick that? So this rate is 1 a minute. This rate is 1 a second. So it's not really strange, it's just unusual, but it makes sense. So if we move to 1 a second reporting, what would it look like in our network? And then let's go faster. Or let's just dial that knob up until the system breaks. Operations characteristics, I think I didn't have any explicit goals there. What I wanted to do was experiment with what's it feel like to set up a cluster? What's it feel like to roll out new versions of software? Will this work in our ops environment? I was going to come here and tell you that it's awful in ops and you shouldn't do it, but Jamie talked me out of that yesterday by showing me how, with save points, I actually can make it work in our network. So Flink, that is. Our thing, again, I told you we have got this kind of adequate operation story. But, and it looks like we might have similarly adequate or maybe better story with Flink. This is the way the system looked, the experiment system. What I did is I set up basically a clone in AWS with its own Kafka. I pulled data out of our staging network. We use our staging network to monitor our production system, and we are a big customer of New Relic. I don't even think we'd be in the top 50. But our traffic here is about, well, we must be in the top 50 because we're about 1% of production. So it makes for a pretty good model for saying, if I take this, run that traffic through an experiment, and then say, well, if I scaled that by a factor of 100, that's what production would look like today. But in 9 months, that'll be half of production. In terms of AWS configurations, these magic code words actually are important because they constrain things about your system that are going to come back to get you. Our Kafka cluster is small, but it's got a lot of I/O. For our baseline system, this is pretty similar to what we have in our data center. We run Docker. So we set these guys up this way. These are 3 16-core, 64-gig machines, but they're a little bit starved on bandwidth. For Flink, I used the same thing of 4 of them. And for Spark, I just used AWS EMR because it comes with Spark. Pretty straightforward. Kafka, we run 0822 in our own fork that we backported some changes to. The reason that that's interesting is that there's features in .9 that might be helpful, but we don't have them. So I can't experiment on a Kafka network that contains capabilities that might influence the outcome of the experiment. So we just basically clone the same thing. And I have a very limited number of partitions for our traffic. It's possible that this is too few. It'll come out later, but it's perhaps that if we had used more partitions, the baseline system would have performed better. This load driver, its job is really to have a dial. So we take input from the system in our data center, and then we dial it up. And we dial it up really by just repeating it. So we take the same message that got sent, and then if you want 200%, we send 2 copies. And if 6,000%, we send 60 copies. So it's pretty straightforward. They all are identical, so they all have the same event time. They'll be in order. Nothing magical is going on there. But it turns out that maybe something magical should have been going on there. This is a very simplistic model, but it doesn't stress all the dimensions that we might want to see. For example, we don't really get different IDs. And that may have influenced the outcomes for Flink and Spark in terms of ID space. And in terms of the baseline system, Maybe. I'm not sure if that key space thing would be important or not. So let's talk about our baseline system. This is a bunch of Java code that we've written. It uses very simple Kafka consumers and producers. And we take a thread. This is a thread. We have it consume a partition or multiple partitions. It aggregates by the agent, the actual agent that reported, and then it does that same aggregation for all of the applications that were reported in that agent. So if you get, say, a time slice here, you'll get, and there's one application view of it, you'll get a time slice there too. But if you get a second agent with the same application, you get that there, but it gets aggregated into here. All of that gets stored in some hash tables, and another thread comes by every minute, pulls the ones that are ripe, in terms of ripe being the time has passed, and it publishes it downstream. You can see, like, this is actually the throughput of that system. It's reasonably quick. It's doing a few hundred. But this is the part that's kind of interesting. This is, if you scroll that page down some, you can see a breakdown by servers. And what we see here is that we see one server that is nominally twice the load. And this is because of a couple things. One is imbalance in Kafka partition assignments, and another is due to the way we partition traffic. We don't have a key mapping hashing system like Flink and Spark do. So what we do is we steer traffic by putting it into the correct partition at the producer. It's a model. I hate it. It was there before I got there. The math around it is awful because the traffic loads across partitions are not very uniform. And there's not much you can do about it because when you put traffic in a partition, one thing is going to read it. So in our model, I'll go back to this picture. In our model, if this partition has twice the load of this partition, then this thread does twice the work. So this thread can be idle, and there could be multiple threads here. If you run out of partitions, they're just going to be idle. So we haven't built the system to spread the traffic around once it gets in. We have other parts of our network where we do that, but it's not in this application. And I didn't want to change this application to perform better. We are going to, but I didn't want to change it to perform better at this point because I wanted to do the baseline evaluation. Okay. So like I said, distributions aren't friendly. This is a CDF of the number of time slices that we see in those reports. And I don't know how familiar you are with reading these kinds of charts, but let me point out a couple things that are interesting. One is that, like, it's dominated by a small number. This here is like 45 or 50. So we'll see a good 90% that are 45, 50 or less. But it's got this horrid tail. So this tail is what causes those threads to have to do a lot of work. And you can see, so you can see from here that that this kind of average is high because of the tail. But the geometric mean and the median are kind of lower because they're dominated by this spike that's around 45 or so. Everything at New Relic, this is one of the things I learned. I've been there a couple of years. One of the things I learned right away at New Relic, everything at New Relic is power law distributed. So we've got 10 customers that are responsible for 60% of the data that we see. And then 45,000 that are there for the rest. These peak load things are problematic, as well as LongTails. Flink we configured very simply. We have a job manager and 3 task managers with 16 slots. Did anybody attend Ted's talk yesterday about faster with Flink? And it's very interesting that he would have, I think his recommendation was that we would put only 3 slots on here and let the system do more work with those. I'm not sure. That's the code. This is one of those awesome things about Flink is that the code to describe the topology is so small. I buried a few things. We've got a fancy deserializer because we've got this ugly serialization model. And I just pulled the mappers out, but the mappers aren't really doing anything interesting. One thing that we do differently in the Flink topology is that we spread the data out by metric. So now if you get a package that's got 4,000 time slices in it, 4,000 different metrics, that turns into 4,000 keys. But that gets spread out across the cluster. So we've got 48 threads that can work on those and spread them out. Whereas in the incumbent model, that all stays in the same place. This visualizer is really nice because it gives you a way to see the topology. What we have, we do a rebalance after the Kafka read because we're only going to read from as many partitions as there are. There's a hashing to the window operator. So the window runs for a minute, and then we get another window over here which rebundles the packages up in that form that I showed you before. So the output here is keyed by account agent and metric ID. But the output over here is keyed by account and agent. So we got to collect all those metrics together and spit them out. That worked really pretty well. A little futzing with time windows and that, but it worked pretty well. With Spark has a similar setup to the Flink model. We've got a master and 3 slaves. The Spark code is also kind of equivalently small, although noisier with types. Not sure if that's because they just haven't done a nice enough job of figuring out good types for streaming or not, but just the type signatures are a little nicer in Flink. That's totally subjective, so I don't think you can decide on that. But and producing the Kafka is awful. There's this horrible dance you have to do with pooled providers and borrowing, and it's awful. But it's awful in a different way, which is there's no event time. Like I could make event time work, I guess, but it didn't work out of the box. And what that led to was, I abandoned Spark, but mostly because Spark generated wrong results. Things got aggregated incorrectly based on their arrival. And that's just the non-starter. So it doesn't matter how fast it is, it's wrong. Let me go through the results relatively quickly. So at 100% load, kind of our standard staging load, nothing interesting, everybody's fine. At 500%, we get, I have totally abandoned Spark because so I'll get 5 times the number of wrong answers, it doesn't matter. At 4,000%, what ended up happening is the Flink system just kept going. It's all good. This system, though, ran out of gas. And it ran out of gas in computing. So we've got Kafka lag. It just couldn't keep up. So that kind of gives us a view of we got about a 5x headroom before we need to do something different. And then at 6,000%, we actually kind of ran Flink out of gas, but not because Flink ran out of gas. We just ran out of bandwidth. There was no Kafka lag, so the Flink system was consuming everything it could get. But if you might not remember, but the systems that we used here, they were limited to 2 gig network interfaces. So I think if we had a fatter network pipe, we would have seen more throughput. I think this is a very promising sort of story for Flink with respect to our application, in that we can go here, the system is very straightforward, and we don't have to worry about performance. Really? Okay. So here's some opportunities to improve the experiment. As I said, more bandwidth. I don't even know where the limit is on that Flink system. This is 3 hosts and 48 cores. It's not really that giant of a compute platform, but we could run a lot of traffic through it. We really should explore this space, this key space. I think this is an area where Flink performance may have some impact. If our key space explodes, does this turn into something? From our perspective, what that looks like is we get more customers, we get bigger customers, we get customers that behave a little differently. We're going to see an explosion in the key space. As I said earlier, this is kind of hard to do. This is hard to fake the data appropriately, but it might be worth experimenting in. And then the last thing that maybe we should do is we should look at database syncs along with the Kafka syncs. So we need the Kafka syncs because downstream traffic wants to process that. We have an alerting product that taps right off of that output stream. But we'd also like to be able to store it kind of more natively. I'm not sure if that would work well or not work well, but it's an experiment that we would like to perform. Okay, I've got a little bit of time, so let me go through. So I tried this just because I thought, hey, wait, that's pretty interesting. If we can combine those two things, then we cut out a bunch of servers that really aren't doing very much. In terms of code, it was really pretty simple. We already had a stream that had the content of that Kafka topic that was in between those servers. So I just tapped onto that stream, rekeyed it, changed the window to an hour. Somewhere in there it says that, 60 minutes. I don't know if you can actually read that. And then did the same thing that we did above, which is do a fold to do the aggregation and then repackage them out onto the other Kafka topic. And in terms of the visualizer, what you see is this is the new stuff. This whole thing here is just what was in the other app. I didn't get a chance to run it, but I ran it on my laptop, so it seemed to work okay. So, thank you. There's time for some questions. Where's my pillow? Where's my pillow?
Yeah, the pillow is there.
You told me I was supposed to throw a pillow at people.
Anybody has a question?
Yeah, any questions?
Thanks for the talk. I would be really interested in how Spark Streaming would have done just in terms of performance. Okay, it's wrong, but it would have been really nice to see whether it can keep up or not. And I understand that even 3 large machines in Amazon can do your load. Have you considered adding a couple of machines and scaling the experiment up a little bit?
With respect to Spark, yeah. So I appreciate that. I mean, it would have been interesting, a bit academic, so I can get more wrong answers. I mean, that was sort of the perspective that we had on it. It might work for other applications that we have, but it doesn't work for this one. With respect to scaling the system, for our incumbent, it wouldn't have mattered. It turns out that we had a bunch of threads that were starved out because there were too few partitions. And having more of them starved out, that wouldn't have helped us. And for Flink, having more systems, if we had said, let's say I had, instead of 16 core machines, I used 8 core machines. So in AWS, that's really simple. But I had twice as many of them. I think we might have seen more throughput through Flink. Because of the bandwidth limitations. It's hard to know the balance in Flink between internal bandwidth and external bandwidth. Like, what am I pulling from Kafka versus what is Flink shipping around among the various task managers? But that's an interesting perspective. I think the thing we're going to work on next, though, is that key space problem.
Thank you.
Thanks for the talk. One question, I think an interesting follow-up would be to see how low you can scale the resources. You keep the same input and you keep removing resources from the Flink job and see how many resources you can remove until it cannot keep up with the data anymore. That would be an interesting thing, I think.
Yeah,
because that saves money in the end.
Yeah, and I don't know, AWS customers out here, like turning off machines definitely saves money. Yeah, I think that is an experiment that's pretty easily done because I can just turn one off and see what happens.
I've got a question. Which version of Spark did you use?
I used 2.0.0. It just came out. I mean, not that long ago.
Because I think that there are options to use time of event in structured streams in 2.0.0.
I couldn't find it in the documentation, and I'm not a Spark expert, so I built a pretty naive implementation of Spark.
Okay, thanks.
Hi, thanks for your talk. I had a question related to your metric ID. How do you deal with collisions? Because you take a 64-bit hash of the metric name, and then you use that further down in your Flink topology as the key. How do you deal with?
That's a great question. We don't. Realistically, we don't.
That's a great answer.
I did ask that same question. I ran a test. I just kind of took all of the metric names that we have. We keep them all in a database because everything goes into a database. We have them all in a database. I ran the names through the hasher, and we had one collision in an area where it was not in the same account. So in terms of how our metric and data is set up, all the data is partitioned by account. So metric name collisions between accounts are irrelevant. Collisions within an account, that would be interesting. This collision couldn't have happened inside an account because they were two different styles of application. I guess they could have happened if it ran into it, but it seems unlikely. So, and this is over some 600 million different metrics. So we were in pretty good shape.
Thanks.
Hi. So what was your reasoning behind picking Flink and Spark? So there's Storm out there, there's Samza out there, there are other quite popular options.
Yes. So our application is relatively similar to Samza, not exactly, but pretty similar. So I felt that was kind of characteristic of that, although if you looked at the proposal, you would have seen that Samza was on the list. I just didn't get time to do it. You mentioned a couple others, like Kafka Streaming.
Of course, Storm is the obvious contender here.
Yeah, we had already discounted Storm because of the lack of exactly once. Although Poseidon, there's some hope that Poseidon does it, but we were never able to actually get any of our prior experiments to work. I think that kind of covers it. I'm a Flink proponent, so that's why Flink was in the list. And Storm is there because that's the obvious alternative. All right, I think we're out of time. We got any more questions? Okay, great. Thanks.
Thank you.